Hello and welcome to lecture 54. We are discussing about Turboprop engine. This course is NPTEL online certification course on aero engine gas turbine cycles. In last lecture we were discussing about different configurations of Turboprop engine. In detail we have discussed about 2-spool configuration. We also have discussed about the 3-spool configuration. And we realize there are different kind of configurations which are possible with in terms of how my spools are connected with the compressor. And for compressor also we have seen there are different possibilities. Some of them they all have all axial flow compressors. Some of them they are having combination of axial centrifugal compressor. Some of them they are having say all centrifugal compressor kind of configurations which are possible with. And we started discussing about one numerical where the information given, as we have already discussed, we have information in terms of say temperature and pressure, that's what is ambient condition. The aircraft, that's what is flying at say 320 kilometers per hour speed. We have our efficiencies in terms of propeller efficiency, compressor efficiency, we have burner efficiency, HP turbine and LP turbine efficiency, mechanical efficiencies, gearbox efficiency and nozzle efficiencies they are given with. The core mass flow rate also is given, that is 2 kg per second. One important parameter given here is inlet total pressure recovery factor. So just remember one thing, what all numericals we have solved as we have discussed in our week 2, we have different configurations possible with different kind of terminologies which we are using for the intake. Till now for many numericals we have taken the parameter called diffuser efficiency. Here in this case it is given with total pressure recovery factor. So it's a different thing. Okay. Same way the maximum turbine entry temperature that is given with, calorific value of the fuel is given, and power split, that is alpha, is given 0.95, and we want to calculate what will be the performance parameter of this engine. And based on this configuration we can plot the line diagram and we can put different stations here. This is what all we have discussed in our last lecture also. So we can put different stations. Be careful what all numbering you are doing here on line diagram for the engine. Similar kind of numbers you need to put on your TS diagram to avoid any kind of confusion or any kind of misconception. Be careful about this part. Okay. Then we have given the hint where we have discussed what all we will be calculating in order to calculate say exit pressure and temperature from different components. We will be doing all our calculation till nozzle because that's what is very important for us in order to calculate the thrust. Then at the same way we can calculate other parameters which are defining the performance of this engine. So let's start with, so very first component we have is our intake. For intake, since it is flying at certain altitude where static pressure and temperature they are given with, and it is flying with some Mach number. So let's put this in terms of our velocity. This velocity it says 320 kilometers per hour. We can convert that into meter per second. We need to calculate what will be the flight Mach number based on our flight speed and temperature. Since the numbers are given to us, we can calculate the flight Mach number to be 0.28. You will realize very soon what is the reason why we are calculating this Mach number. Now let's see how we will be doing the calculation for the intake. For this intake we have information about static pressure and static temperature. Our requirement is total pressure because we are given with the information, it says total pressure recovery factor, and that's what is a ratio of say P02 by P0 infinity, and that's the reason why we need to calculate P0 infinity. Okay, so let's put these numbers. Since my pressure, that's what is given 38 kilopascal, My gamma value is 1.4, Mach number we have calculated, it is 0.28. This is giving the inlet total pressure as 40.13 kilopascal. Now, since we have information about diffuser pressure recovery factor, it is 0.98. Let's put this, it's a ratio of P02 by P0 infinity. If we put these numbers, it says our exit pressure is coming to be 39.32 kilopascal. So this is the pressure with which flow is entering inside the compressor, we can say. Now temperature we can calculate, it is T infinity into 1 plus gamma minus 1 by 2 m infinity square. If we put these numbers, my temperature is coming 246.81 Kelvin. Okay. Now let's look at what is my next component here. So we can say we have calculated till station 2. Let's look at the next component. It is my compressor, and for compressor we are given with say pressure ratio of 6.3, and here be careful, it is given PC, that is nothing but the polytropic efficiency of the compressor, and this polytropic efficiency is 84%. Be careful. This is not the adiabatic efficiency or isentropic efficiency. It's a polytropic efficiency. Polytropic efficiency we have defined earlier. It is per stage efficiency. Okay. So let's look at how do we proceed with. So pressure ratio we are writing as P03 by P02. It is 6.3. So exit pressure from the compressor, that is 247.74 kilopascal. Now let's try to calculate what will be the exit temperature. So from the polytropic efficiency correlation, what we know, my pressure ratio, it is a function of temperature ratio to the power gamma into polytropic efficiency divided by gamma minus 1. Okay. Since here in this case we are given with the pressure ratio, this pressure ratio is 6.3, gamma value is known to us, and our polytropic efficiency also is given, and that's what will be giving the exit temperature from the compressor as 461.58 Kelvin. Be careful what information is given, read those informations carefully. This may lead to put you in trouble with the numbers. You can imagine if you are calculating your pressure at the exit of the compressor to be wrong, then all remaining parameters will come different. Okay. So do read the information carefully. This is a special kind of numerical with all we have discussed for last 9 weeks, where we are having this as a variant. Okay. So just look at, maybe for any kind of cycle, this logic what we are using, that can be used for. Okay. Now let's look at the next parameter, next component we have is our combustion chamber, and for this combustion chamber we are given with the pressure loss of 2%. So we can say the outlet pressure from the combustion chamber to be 242.79 kilopascal. Now for this we have maximum turbine entry temperature, that's what is known to us, but our major requirement is to calculate what will be the fuel air ratio, or what is the amount of fuel we are adding in order to raise that temperature. So here in this case, if we will be writing our energy balance equation, that's what we have done repeatedly for number of cycles, what all we have solved with and what all cycles we have discussed. Let it be say turbojet engine, let it be say for turbofan engine, where we have discussed all 8 kind of configuration, let it be for say turboprop engine. So this formulation, that's what will remain same. We are putting this number, carefully check with the units for CP value, and if we are putting these numbers, it says our fuel air ratio is coming 0.023. Okay. Now since we have this information with us, we will be moving with the next component. So next component we have is our HP turbine, And as per the configuration, we know this HP turbine, that's what is used to rotate the compressor only. And that's the reason we can write down the work balance equation as work that's what is developed by HP turbine will be consumed by the compressor. Let's put in terms of mechanical efficiency, and we know this work by HP turbine, it is given by m dot infinity into 1 plus F H04 minus H04.5. Here if you look at, this is what is representing the exit condition from the HP turbine, and that's what is equal to m dot core into H03 minus H02. Since we have our information available with us, so we will be writing down in terms of Cp value, and if we put all these numbers, it says my temperature at the exit of HP turbine is 1027.26 Kelvin. So this is what is the temperature from the HP turbine. Do not get confused in terms of doing the calculation. I know many of you might have committed mistake here. Be careful. What is the use of HP turbine? This HP turbine here in this case is used to rotate only compressor. In earlier numerical, what we have seen, my turbine, the gas generator, that's what is used to rotate both compressor as well as the propeller. Okay, so this is somewhat different with. Now since we have our exit temperature, we can calculate our exit pressure from the turbine. We have equation for the efficiency. So this efficiency we are correlating in terms of my expansion ratio. This expansion ratio, if we are putting the numbers, my pressure is coming as 109.48 kilopascal. So this will be the pressure from say exit of my HP turbine. Till here you should not feel any discomfort. Okay. Now let's move towards the next component. Next component we have is our power turbine, or you can say this LP turbine. That's what is used to rotate the propeller. Now what is the beauty here? So here if you look at carefully, since we are not having the straight information available, no doubt it is given with say power split factor to us. This power split factor, that's what is being used for LP turbine as well as for the nozzle. So let's try to write down the value of this power or ideal power. So this ideal power we can write down, that is given by m dot core 1 plus F H04.5 minus H09S. This is the enthalpy here. So if we are putting these values, then this is what has been given in terms of our equation. Okay, let me simplify this equation. It says this is what is the ratio we are representing in terms of pressure ratio P9 by P05. Okay, now let's look at this same. What we are discussing is we are given with the number, it is say my power split factor and the efficiency. So this value we can put in a different form. What will be the different form? Just look at here. It says this is given by my power of LP turbine, it is m dot C 1 plus F. This is my efficiency of the LP turbine into factor alpha, and this is what is my power input or delta PE. Do not get confused in terms of solving this numerical. Just look at carefully, try to understand this numerical. Okay, so here we are discussing about this point, this. Okay, this is what is my PLP turbine. Okay, that's what is my actual configuration. My ideal configuration will be somewhere here, and that's the reason why we are multiplying it with say my turbine efficiency into my factor alpha. Let's put all the numbers. If we will be putting these numbers, my power for LP turbine, that is coming 478.23 kilowatt. So this is what is a power, that's what is been required in order to rotate, or say in order to use that for rotation of our propeller. Okay. Now, what is the next component we have? It is in terms of the calculation of the power. From this power, we can write down in the form of enthalpy. From this enthalpy, we can calculate what will be my exit total temperature from the LP turbine. Since we have power value, that's what is known to us. Be careful, what all power we have calculated is in terms of kilowatt. You need to convert that into watt. And if we are calculating this T05, it is coming to be 824.46 Kelvin. So this will be the temperature at the exit of LP turbine. Similarly, we can calculate what will be the pressure. So this pressure, as we have discussed earlier, can be correlated in terms of pressure ratio and our adiabatic efficiency. The efficiency for LP turbine is given as 90%. So let's put that number. It says my pressure, it is coming 40.35 kilopascal. So this will be the pressure with which flow will be coming out from the HP turbine. Okay. Now let's look at the next parameter. What we have is our nozzle, and for nozzle, what all information we have is the entry condition. It is known to us for the nozzle. We know in order to do the calculation for exit velocity, we need to calculate exit static pressure, exit static temperature, and for that we need to go with the logic. What is our logic? We need to calculate critical pressure ratio. Based on that critical pressure ratio, we need to decide whether our nozzle is choked or unchoked, and based on that we need to decide what will be our exit static pressure. So here in this case, my critical pressure ratio, it is given in terms of nozzle efficiency. This nozzle efficiency is given 98%. Gamma value for the gas, it is given 1.33. Based on that, we can calculate the critical pressure. This critical pressure, if we look at, that is coming to be 21.5 kilopascal. This critical pressure is lower than that of our atmospheric pressure. So we can say this nozzle is unchoked nozzle. And what will be our exit pressure? This exit pressure will be our ambient pressure, and that's what we are taking as 38 kilopascal. Okay. Now based on that, we can calculate our exit velocity. This exit velocity, that is given in terms of my pressure ratio. So if we are putting these values, it says exit velocity is coming to be 165.93 meter per second. Okay. Now since this exit velocity is known to us, we will be calculating what will be my 9i. What is that and why we are calculating? Let's look at what is the reason behind that. Here in this case, we can write down my ideal condition, that's what is isentropic process, that is given by T05 by T9i. It is in terms of my pressure ratio. So that's what will be given my 9i condition. And from our efficiency correlation for the nozzle, we can write down the efficiency is given by H05 minus H9 divided by H05 minus H9i. There is a specific reason behind it, because what all we have calculated, it is our ideal power. We are talking about delta Hi, and that's the reason why this 9i point, that's what is very important. So let's try to calculate the point 9, because this point 9, that's what is representing my exit condition from the nozzle. So if we put these numbers, my exit temperature is coming 813.50 Kelvin. Once we have this, we can calculate our exit Mach number, and flow exit Mach number is coming 0.3. It is a subsonic condition. Okay. Now we are of major interest in terms of performance parameters. So let's recall what all are the performance parameters from the turboprop engine. We are interested in thrust, both the thrust, propeller thrust as well as core thrust if it is there. We are interested in thrust specific fuel consumption or equivalent specific fuel consumption based on power. We are interested in calculating what will be the thermal efficiency, what will be our say propulsive efficiency, and what will be our overall efficiency. So let's try to calculate first the propeller thrust. This propeller thrust, as we know, it is represented by T into V. That's what is equal to this efficiencies into say power into LP turbine power. So if you go through our earlier lectures where we have discussed about the efficiency terms, that's what is starting from say turbine to compressor, from compressor to say gearbox, and from gearbox to the propeller. That's how these all terms they are coming with. Okay, so do not get confused here. So these all efficiencies they are known to us, so we can calculate what will be the thrust generated by this propeller. And if we are calculating that, the thrust generated by the propeller, it is coming to be 4.21 kilonewton. As we have discussed in earlier class, this propeller thrust can be calculated by many ways. It's all depend on what all configurations we are having and how people they want to do their calculation. They already exist with the propellers, they want to fit a specific kind of propeller, then propeller characteristics are important. Based on that propeller characteristics, they will be calculating what will be the power requirement, and based on that also you can calculate what will be the thrust requirement. Okay, but for this course dedicatedly, we will be calculating based on these fundamentals only. Okay, now let's move towards the next thrust. We are not having any information, but if we look at it, says our exit velocity is coming to be 165.93 meter per second, and we know that's what is not a small number. If it is not a small number, that means there will be contribution by this core engine nozzle also, and that's the reason why we will be calculating the thrust contribution by this core engine. And if we put that, it is given by m dot core into 1 plus f v exit minus v infinity. Okay, and that if we are calculating this number anyway, it is coming to be lower 161.73 Newton, and total thrust we can calculate, that total thrust is coming to be 4.37 kilonewton. Okay, now let's look at what we mean by propeller power. This propeller power that can be given in terms of efficiency term, it's a gearbox efficiency into mechanical efficiency of the LP turbine, and power, that's what will be generated by the LP turbine. If we will put all together, it says power required to rotate this propeller, it will be 450 kilowatt. Okay, and if we calculate say power, that's what will be produced by the core engine, that's what is given by T core into V infinity, and that's what is 14.4 kilowatt. There is a specific reason behind calculating this power. Okay, let's see what all are the requirement, because since this is what is a power generating device, we are using this device or this engine for the generation of power. That power we are using for the rotation of the shaft, and that's the reason why here we need to calculate equivalent shaft horsepower, where we have contribution because of both propeller as well as with the exhaust nozzle. So here in this case, this is given by one of the relation here. If you recall, we have discussed this in very first lecture for our calculation. So let's put these numbers. If we are putting this number, we have some different parameter. One of the parameter, that is to convert the kilonewton to the pound force. Same way meters per second to miles per hour. Okay, same way kilowatt to HP. These all are the conversion factors, and if we are calculating, it says my equivalent shaft horsepower, that is given by 626.77 HP. Many times people they are putting that in terms of kilowatt also, which is multiply that with 0.746, and that's what is coming to be 467.57 kilowatt. Okay. Now this is what is equivalent shaft horsepower. Now let's look at the next parameter. Here we know when we are having say turboprop engine or turboshaft engine, we are calculating the specific fuel consumption. This specific fuel consumption we are putting as equivalent specific fuel consumption. Sometimes people based on the thrust they are writing thrust specific fuel consumption. Since we have calculated thrust, that's what is generated by propeller as well as by the engine. That's the reason we will be putting that in the form. It says thrust specific fuel consumption. It is given by 50.52 milligram per Newton second. Okay. Similarly, say equivalent specific fuel consumption, that's what we are putting m dot f divided by equivalent shaft horsepower. And if we are calculating that, this number with the conversion is coming to be 0.5825 pounds per equivalent shaft horsepower into say hour. Okay. So we need to be careful in terms of say this formulation, what formulation we are using, and we need to remember with the conversion factor also. Okay. Now let's look at with the next parameter, that is our thermal efficiency. Now it is little tricky to define this thermal efficiency, but from our mechanical understanding or engineering sense of understanding, this thermal efficiency we are defining in terms of say output by input. What we are getting in output is equivalent shaft power, and our input, that's what we are putting as say m dot f into q. It's little cruel way of doing the calculation. In open literature, people sometimes they are using this for the calculation of thermal efficiency. So let's use that formula only. Okay. So if we will be using this formula, the thermal efficiency is coming to be 24.20%. Okay. There is nothing wrong in doing calculation by this mean. Okay. Because we are considering the equivalent shaft horsepower. That's the reason why there is nothing wrong in putting this parameter. Okay. Now let's look at with the propulsive efficiency. What we mean by propulsive efficiency, it is in terms of T into V infinity divided by equivalent shaft power. This total thrust we have calculated, our flying speed is known to us, and equivalent shaft power is also known to us. It says my propulsive efficiency to be 83.07%. Okay. Now let's look at the important parameter in terms of overall efficiency. Here if you look at, you will see overall efficiency I am putting by two different ways, because literature says like overall efficiency can be defined in terms of propeller efficiency into thermal efficiency. One other definition, it says my propulsive efficiency into thermal efficiency. So let's try to look at these numbers. We know our propulsive efficiency to be 83.07 and thermal efficiency to be 24.2. That's what is given overall efficiency as 20.1. Similarly, if we do the calculation, our propeller efficiency is given 82%. Thermal efficiency we have calculated as 24.20%, and it says overall efficiency to be 19.84%. So here it's little tricky to understand and put the numbers. Somewhere at initial stage of discussion I say whenever propeller efficiency is not given, you can assume that efficiency to be 80%. Okay. So these are the ways to calculate our overall efficiency also. Now in overall sense, if we put this is what is our cycle, and for that cycle under the cruise condition we have done our calculation for the net thrust, we have calculated equivalent shaft horsepower, we have calculated equivalent specific fuel consumption, then we have calculated our say propulsive efficiency, thermal efficiency and overall efficiency. Okay. Now with this understanding we have idea like how we can do the calculation for turboprop engines. let the configurations in terms of construction be different. Now let's look at very old fashioned what all we were discussing, saying like what all are the performance parameter and how or what parameter they are depending on. Say for turboprop engine, important parameters are propeller thrust, nozzle thrust, propeller power, fuel air ratio, equivalent specific fuel consumption, propulsive efficiency, thermal efficiency, overall efficiency. And let's look at what parameter it depends on. These parameters are what is my say compressor pressure ratio or overall pressure ratio, turbine entry temperature, what is my power split factor, efficiencies of different components, we have our ground condition or the flight condition. So all these parameters, that's what is affecting the performance of say turboprop engine. So let's try to look at one by one. Let's take very first parameter as say pressure ratio. Let me put the plot here. It says this is representing my pressure ratio versus thrust. This is our design point, and if we look at carefully, it says with the increase of pressure ratio, our thrust, that's what is increasing. Okay, and this increase of thrust, that's what is correlated with what all we have discussed in terms of our power. Okay, what will be the power available for say HP turbine, power available for LP turbine, and it also depends on what will be say exhaust thrust. Okay, suppose if I consider say next parameter of our interest, it is specific thrust. We have discussed that's what is correlated in terms of airflow rate. Next parameter let me put as a thrust specific fuel consumption. It says with the increase of pressure ratio, our thrust, that's what will be increasing, and that's what is giving the benefit in terms of decreasing the thrust specific fuel consumption. So it says like if you will be going with higher and higher pressure ratio, we will be having say less thrust specific fuel consumption. Let's correlate that in terms of efficiency. Here if we look at, it says with the increase of pressure ratio, our thermal efficiency will be increasing. Yes, as we have discussed, that's what is correlated with the power. And what is my heat input? My heat input, that's what will be remaining same for all the case because it's MF into CV. But at the same time, what will be the temperature at the exit of my compressor, that makes the difference in terms of work as well as my heat input. Okay. And here this is representing our propulsive efficiency. And in overall sense, with increase of our pressure ratio, overall efficiency of the engine will be increasing with. Can you try with the next parameter? What is our next parameter of variation? We'll say my pressure ratio we are putting same, we are varying the turbine entry temperature. So let's look at what all is your interest or how my turbine entry temperature, that's what is affecting our thrust, specific thrust, thrust specific fuel consumption and all efficiencies. Can you try with pen and paper? Let it be wrong. It will just build your confidence in terms of understanding what all we are learning for last many weeks. Okay, so let's look at here what it says. With increase of turbine entry temperature, we will be having the rise of the thrust, and this rise of the thrust, that's what is correlated in terms of say both the thrust, that's what is generated by propeller as well as thrust generated by our core engine. Okay. Same way if we look at our specific thrust, with increase of turbine entry temperature, we will be having our specific thrust also to be increased with. Let's look at what is happening with the thrust specific fuel consumption. Any guess for that? Okay, what all we have discussed in turbojet engine, what all we have discussed in our turbofan engine, same trend, that's what will be happening here. What will be that? It says here in this case, with increase of turbine entry temperature, we will be having our thrust specific fuel consumption, that's what will be reducing with. Okay, let's look at with the efficiency point. Here this is representing with increasing the turbine entry temperature, our thermal efficiency will be increasing, our propulsive efficiency will be increasing, and that's how our overall efficiency also will be increasing with. Now these two parameters which are common for what all we have discussed earlier, here in this case there is nothing called bypass ratio, there is no configuration in terms of bleed. Okay, we have one more important parameter, that's what is power split factor. So let's try to understand what will be the effect of that variation. So here in this case, let's take the variation of power split factor, putting all other parameters to be same. Let's look at here. If we look at carefully, it says with increase of power split factor, our thrust, that's what will be increasing up to certain extent, and then after that's what is falling down. What is the reason behind the falling down? That's what you can correlate based on this equation. This equation, that's what is representing my alpha both by propeller, and alpha, that's what is because of my core. So this is what is the summation of two thrust, propeller thrust as well as my core thrust. Okay, so after certain value of split factor, there is no benefit in terms of increase of say total thrust. So we need to be very careful in selection of this split factor. So many times when we are doing our cycle analysis, we need to assume this number. There are different ways to solve the numerical. Suppose say power split factor for this numerical, that's what is given. If it is not given, you can assume also. Or you can say you are making your engine, as we have discussed earlier, I don't want to generate any thrust by my core engine. I want to generate thrust only by the propeller. So under that kind of configuration, we can move with say minimum value of my exhaust velocity, and we will not be getting more benefit in terms of having more split of alpha. Okay, so be careful in terms of selection of this parameter. Okay, here this is what is representing my say specific fuel consumption. It says with the increase of the power split factor, we will be having reduction in the specific fuel consumption. That's what is of our interest. And this is representing my propeller thrust to the total thrust versus our split factor. So it says with increase of say power split factor, we will be having more and more value of propeller thrust compared to by total thrust configuration. Okay, so what alpha we will be selecting, that's what will be deciding with what advantage we want to take from our engine. Okay, so for this numerical also, if you go back, revisit the part in terms of thrust calculation, you will realize lot of thrust or higher value of the thrust, that's what is generated by the propeller, and less amount of thrust, that's what has been generated by our core engine. Okay, so that's what is depending on what is our requirement. Let's look at in terms of our efficiency. So here it says by increasing the split factor, we will be having say reduction in the thermal efficiency, but at the same time propulsive efficiency, that's what will be increasing. You can understand there is a specific reason behind that. More and more thrust we are getting from our propeller. What is the indication of that? It says if I am having higher power split factor, that's what is representing more amount of thrust we are interested in by the propeller, and that's the reason why our efficiency, propulsive efficiency is going to be higher. And in overall sense, it says my overall efficiency is not making much difference with the variation of split factor. So what is important, that's what need to be decided with. Okay, so I'm sure you have built the confidence in terms of understanding this numerical. Be careful what all plots we are putting here, that's what is with these specific numbers. So many of you were having say question in terms of how do we put the trend of these plots? That's what you need to literally do the calculation. Suppose here in this case my turbine entry temperature is 1200 Kelvin, 1212 Kelvin. If I'll be moving with the temperature to be say 1400 Kelvin, the trend will be different. Same way, what will be my pressure ratio? That also variation. So there are ample of opportunities you have, ample of plots which are possible with. Now let me put the point here. So when I have recorded with the introduction lecture or introduction part for this course, that time I told this course, that's what will be helping you in terms of future requirement of AI/ML. What we mean by AI/ML is all in terms of collecting lot of data. You need to collect the information with the variation of some parameter, what will be the effect on our performance parameter. Then maybe you need to go with the optimization or maximization of some parameter, and that's where you need to train your data. And therefore training of that data, you need to have a lot of information. That's what need to be available with you. With all this information, you can go with the next step. That's what we say as AI/ML application for gas turbine engines. So here we are stopping with this week lecture. So what all we have discussed in this week is dedicated for the turboprop engines. We have seen different types of turboprop engine, what all are the applications of turboprop engine, what all are the advantages and challenges for this turboprop engines. Then we have solved the numericals also in order to do the cycle analysis. Now in next week we will be discussing about turbosoft engine, and that's what will be giving the new kind of flavor. So with this, I'm sure you are able to differentiate what is a construction difference of turbojet engine, what is a construction difference of turbofan engine, construction difference for turboprop engine, what all are the benefits of different engines. You can understand all engines have their own uniqueness. All engines have their specific applications, and based on that, the engineers, they need to decide with airline companies, they need to decide with aircraft manufacturing companies, they need to decide with what engine need to be fitted with what aircraft. So here we are stopping with. All the best. Let's meet in the next week.